Okay, so today it looks like we're making a two-way table, and we want to be able to find frequencies. Bam, bam, excitement, excitement, excitement. What does this have to do with probability? Well, we'll have to find out. I'm sure it's got to have something to do with probability. Two-way table. It collects data, and that data goes into more than one category. If it's a two-way table, it goes into two different categories. So the categories are separated into rows, which are horizontal, left, right, and columns. Those are vertical, up and down. So let's pretend I wandered around and randomly surveyed middle school students and high school students about whether they think the more awesome animal is a cat or a cow. Well, we all know who's going to win this one, right? It's going to be the cow. So, organize the results. I mean, there's a lot of ways I can do this. Two-way table is just one of them. And so I've got one of the categories is going to be students. And so those are in the rows, right? Because the students could have been in middle school or high school. The other category is which they thought was the more awesome animal. And so those are the columns, those are vertical, the cat and the cow. And, I would have thought the cow would do a lot better. What's going on here? Good grief. Anyway, there's our table. There's our results. Okay, so each entry in the table is called a joint frequency. If you want to know why on earth we call it a joint frequency, well, it's where the two categories meet. Think of your elbow, right? Why is it a joint? Well, two different bones meet at your elbow. That's why it's a joint. Same thing with your knee, right? Your upper leg bones and your lower leg bones meet at your knee. It's a joint. Or if you're into construction and you're going to frame a house where the studs meet the plates, that's a joint, right? Because you've got different boards meeting, and you use nails or wood screws or sometimes even steel plates at those joints. So, for example, that 11 is a joint frequency because it describes in part the middle school students, but it also describes in part like cat as being the more awesome animal. So each entry is a joint frequency. Now, of course, grand totals are usually nice to work with. So this way I can tell that, hey, if the 11 middle school students like the cat, 2 middle school students prefer the cow, there are 13 middle school students that I talked to, right? Or if I want to look at, well, how many students thought the cow was the more awesome animal? Well, 2 from middle school, 9 from high school, that adds up to 11. And then notice that 29, the grand total, has to be consistent. So if I add up the 13 middle school students and the 16 high school students, I get 29. Same thing for the more awesome animal. If I add the 18 cat and 11 cow, that also better add up to 29 because I talked to 29 students that gave me an opinion. So those are the marginal frequencies. Again, we don't call them marginal because they're lesser. We call them marginal because they are on the margin, right? They're on the edge, the outside. So the joint frequencies are the inner part of that table. And then the marginal frequencies are kind of like our totals and grand total. This is what's got to do with probability. right? If I sample students, take a little survey, I can then sometimes extrapolate that into a larger population and say, hey, my hunch is. So if I went up to a student at random, what would be the probability that they thought the cat was the more awesome animal? Well, it looks like I talked to 29 students. 18 of them thought the cat was more awesome than the cow. So if I just went up to any old student, I would expect the probability that they would think that the cat is more awesome than the cow 18 out of 29 times. What is the probability that if a student was in middle school that they thought a cat is the more awesome animal? 11 out of 13. Now notice I'm not using 29 as my denominator, right? Because the requirement is the student had to be a middle school student. Why I only talked to 13 middle school students. So of those 13, 11 thought the cat was more awesome than the cow. What is the probability that if a student thought a cow is the more awesome animal, that the student is in middle school? What will I use for my denominator this time? Well, it's contingent that the student had to have selected the cow over the cat. So I've got to use 11 as my denominator because I've got to be under the cow column. And then for the joint probability, or I should say, the joint frequency, there were 2 middle school students that selected the cow. So 2 out of 11. Now this is still a two-way table. That doesn't mean there's only 2 categories of students or 2 categories of favorite color, right? It's a two-way table because I'm looking at students as one category. I'm looking at favorite color as another category. But here, students are broken down into 6th grade, 7th grade, 8th grade. Favorite color? Mysteriously, no one picked like red or blue or anything like that. But holy cow, they sure like their orange, purple, and green. And so let's take a look at this table and answer some probability questions off of this. Oh. I wonder how many 8th graders chose green. How would I ever figure out how many 8th graders chose green? Well, let's systematically go through this table and let's see if we can fix it. Well, I can figure out how many 6th graders there are, because 8 plus 2 plus 1 adds up to 11. I can now figure out the grand total number of students, because 11 plus 16 plus 14 makes 41. I can now figure out the grand total for green, right? 17 plus 18 is 35. So 41, take away 35, has to be 6. Now I can figure out how many 8th graders picked green. It had to be 2, right? 1 plus 3 is 4. 2 more makes 6. Now that's not the only way I could have gotten there, right? I also could have started by figuring out how many 8th graders picked purple. And then if I know how many 8th graders picked purple, I could have then figured out how many 8th graders picked green. So there's also more than one way of filling in these blanks. But if you're ever confronted with a partial table, the first thing you want to do before you try and answer any probability questions is figure out, well, what numbers are missing, what should go in those blanks. Can you figure out the exact number that belongs in there? Okay, what is the probability that a seventh grader chose purple? Now, with more columns and more rows, it sometimes gets a little trickier making sure I can figure out what number needs to be my numerator and what number needs to be my denominator. Right, so I'm like, okay, the student had to be a seventh grader. So make sure I'm looking in that row. 9 chose purple, 16 grand total. Probability that a seventh grader chose purple, 9 out of 16. What is the probability that chose purple? How about, oh no, okay, what is the probability that a student that chose purple is a seventh grader? Okay, it's written correctly, I just can't read it. What is the probability that a student that chose purple is a seventh grader? No, it's not going to be the same fraction. I know we're still talking about seventh graders. I know we're still talking about purple. But this time, the condition is they had to have chosen purple. Right? They had to have chosen purple. What's the probability that they're a seventh grader? Well, of the 18 that chose purple, 9 were seventh graders. And of course, 9 over 18, we're going to reduce that fraction. We're not going to leave it as 9 over 18. Right? Always reduce the fraction when possible. What is the probability that a student is an eighth grader or chose orange? Okay, first I'm going to show you what you don't do. You don't grab the grand total for eighth graders and the grand total for orange and add them together and get 31. That is not what we do here. I'm going to give myself a reminder in the corner. Okay, I'm going to put the no 31 down there in the bottom left corner. What should I do instead? Well, I need every student that either selected orange or they are an eighth grader. And each of those entries is what needs to be added together. And so notice I've actually got 26, not 31. Right? I don't want to count the eighth graders that selected orange twice. Right? Those 5 students should only be counted one time each. And if I just go off the grand totals for orange in 8th grade, those students are being counted twice. Right? Each student needs to be accounted for exactly one time. So 26 students are either 8th graders or they selected orange. Again, in math, this is kind of weird. If they're both 8th graders and they selected orange, it counts as an OR. And of course, there were 41 students altogether. So the probability that a student is an 8th grader or chose orange would be 26 over 41. Of course, we talked about independent and dependent events on, I believe, the previous PowerPoint. And that's what's going to be a subject of the IXL today. I still think that cows are the more awesome animal in comparison to cats. But obviously I'm in the minority, as it looks like more of you think that the cat is the more awesome animal compared to the cow.